Okay, let's continue the discussion of section 5.1. Polynomial functions. Continue. Okay, so last time we stopped at an example. We have this fx equal to x squared x minus 2. X squared x minus 2. We study the x-intercept, y-intercept, and we get the graph. The graph is more or less like this. Here's 0, here's 2, here's 1. Okay, and we came up with a conclusion, like observation. So here 0 has a multiplicity 2, 2 has a multiplicity 1. So we get the conclusion: if R is a 0 of even multiplicity, like this, even multiplicity 2, 4, 6, 8, then the graph touches the x-axis. Okay, so like this it will touch the x-axis. And second, if R is a 0 of odd multiplicity, if you have an odd multiplicity, then the graph crosses the x-axis. Crosses, like from negative positive or positive to negative. Okay, so we stopped at this observation. This is correct, but so far we cannot prove it. We take them for granted. And even though when we know it touches x-axis or cross x-axis, we want a detailed description. So we want to see the behavior near 0. What is the behavior near 0? So let's check here. We still use this example. So fx is equal to x squared times x minus 2. So we first study the 0. 0 is a 0 of multiplicity 2. Okay, so the number 0 is a 0 of the polynomial of multiplicity 2. Okay, near 0. Near 0, of course, x squared will be close to 0, but x squared is the main term because it vanish. But near 0, x minus 2 is close to negative 2. Okay, so this number is close to a non-zero number, negative 2. So fx is going to be approximated by negative 2x squared. So when x is near 0, fx is close to negative 2x squared. So this is a 0 term. 0 term, you copy it, and you estimate the rest of the non-zero terms. 0 minus 2 is negative 2, so it's close to negative 2x squared. So that's why negative 2x squared is like this. So that is the reason when we try to sketch the graph of this original function close to 0, when it is close to 0 in a very, very small neighborhood, it looks like this. Okay, so that is a behavior near a 0, near a solution. Okay, so that's the possibility when you study the 0. And the number 2 is a 0 of multiplicity 1. Okay, Okay, so x minus 2 to power 1. Okay, so near 2, near this quantity 2, near this 0, 2, x minus 2 will be kept, and you studied x squared. X squared is close to what? 2 squared is 4. So fx, when x is close to 2, is almost, you see, x squared is close to 4. You replace x squared by 4, you'll get 4 times x minus 2. 4 times x minus 2 is like this. So that's why if you check this check the behavior function close to 2 in a very tiny region, it looks like a straight segment with a slope 4. So it is straight segment with a slope 4. Okay, so that is like the supporting evidence for us to sketch the graph. Here it must be like this shape, and here it has to be a straight shape, a straight segment. So this is so-called the behavior near 0. Behavior near 0. Okay. So let's do another case. For example, if we have fx equal to x squared, x minus 2 cubed. Let's assume it is a cubed. If it's cubed, it's an odd number, so 2 is a 0 of multiplicity 3. So the graph will cross x-axis. How? And near number 2. So again, this term will be kept. This is related to 2. And here, this term will approach 4 again. X squared is close to 4. So fx is close to 4 times x minus 2 cubed. So what is 4 times x minus 2 cubed? The cube function looks like this. Remember that we had the demonstration. So when you try to sketch the graph of x squared times x minus 2 cubed, you have to, when you approach this number 2, position 2, you have to draw the sketch like this. You cannot draw straight segment. Straight segment is not the proper demonstration because it looks like this one. Okay, so that is the behavior near a 0. Okay, so we get the conclusion. Conclusion 1, the multiplicity of a real 0 determines whether the graph crosses or touches the x-axis. Crosses or touches the x-axis at 0. Okay, so it will touch or it will cross. And the argument we just had, behavior of the graph near a real 0 determines how the graph touches or crosses the x-axis. So it will give us a detailed information about this, about the curve in a small neighborhood. much more detailed information. It's not a straight segment. It has to be like the uh, the the cubic function. Okay, so that's the behavior near 0. Okay. Okay, so we have multiplicity and behavior near 0. And another thing, check here. You go up and down and up. So at this point, left side is increasing, right side is decreasing. This point, left side is decreasing, right side increasing. So at this point, the increasing, decreasing changes. Or in other words, we say the graph changes the direction. If that happens, we call that point turning point. Okay? So the points at which a graph changes direction are called turning point. Turning points. So basically this function has two turning points, 1 and 2. This is not. It's still the same direction. It go up the same direction. Only this point and this point, they are turning point. Okay, so we're talking about the geometry. We try to understand the detailed information from the graph from the geometry. Then we are going to mention a theorem without proof. It's about the number of turning points. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. Okay, so if you have a polynomial with degree n, then it can only have at most n minus 1 turning points. You cannot have a lot of turning point. That number is controlled by n, then it should not be greater than n, greater than or equal to n. Okay, so this is when you know the number, the degree, you can determine the turning point, the number of turning point. If the graph of a polynomial, we'll only talk about polynomial functions. Other functions, the number of turning points are not controlled by this theorem. If a graph has n minus 1 turning point, if it already has n minus 1 turning point, the degree of f is at least n. Is at least n. It's the same idea, same meaning. Okay. So this is a theorem about the number of the turning point. The number of the turning point cannot exceed the degree, cannot exceed or equal to the degree. Okay. Okay, now let's see some example. The first, assume we have several graphs. If you have a graph like this, then this graph cannot be the graph of any polynomial function. Why? Because we know polynomial function has smooth and continuous graph. So this is not continuous, not continuous. Okay? So it does not satisfy this condition. And second, if we have something like this, okay, if we have a graph like this, we will see first it is continuous and smooth. It is possible. It can be the graph of a polynomial function. Okay, so first of all, it can be, and second, we can say more. It has 3 zeros. Has 3 zeros, the degree is at least 3. So here, 3 zeros, degree is at least 3. 2 turning points. So it also implies a degree is at least 3. So 2 conditions both imply the degree is at least 3. So it can be the graph of a polynomial function of degree at least 3. It can maybe 3, 4, 5, 6, whatever. Okay. If this happens, cannot be the graph of a polynomial function. Why cannot? Because it's not smooth. Has a corner. A polynomial function must have a smooth graph. Okay, smooth graph. This one. Okay, for this function, first it can be the graph of a polynomial function. And now let's see the degree of degree. Here you have 2 zeros. 2 0 at least degree 2. 2 0 at least degree 2. But it has 1, 2, 3 turning point. 3 turning point means that at least degree 4. 2 zeros. At least degree 2. 2 zeros at least degree 2. 3 turning points implies at least degree 4. You must add 1. You must add 1 to the number of the turning point. So you satisfy these 2 conditions, degree at least 4. You cannot select the 2. You have to satisfy both. Okay, so you see 2 zeros and 3 turning point. Turning point, it changes the direction. Here is up, here's down. Here's down, here's up, and here's up, here's down. Okay, so you choose that large degree to satisfy both conditions. Okay, so this is a way to apply this turning point condition and relate it to the degree of the polynomial. The turning point, the number of the turning point is less than or equal to n minus 1. Okay. Like the behavior near 0, let's see, still the same polynomial, x squared x minus 2. We want to study the behavior when x is far, far from 0. Okay, so first let's multiply it out. It's x cubed minus 2x squared. X cubed minus 2x squared. And we factor out x cubed. We factor out x cubed, the leading term, the highest power. And then we will see that when ops value of x is very large, when ops value of x is very large, 2 over x is very small. 2 over x, you have a large denominator, it makes your fraction small. The numerator is fixed. So 1 minus close to 0. So 1 minus 0 becomes 1. So fx is more or less like x cubed. More or less like x cubed. So this is the behavior when x, ops value of x is very large. And we call this the end behavior. It's end behavior. It's end behavior. When x is extremely large to the positive infinity or to the negative infinity, what is a simplified version of fx? Okay, so from this observation, you see here we always factor out the term with the highest power, with the degree. So that's actually the proof of the theorem and behavior and the behavior theorem. So for large value of x, large value x, either positive or negative, the graph of the polynomial function fx is a(n)xn a1x a0. This fx resembles the graph of the power function y equal to a(n) x2n, just the leading term. When x is very, very large, you can only consider the leading term and ignore the lower terms. So for example, if we have this fx equal to negative 2x cubed plus 5x squared plus x minus 4, whatever. But once you determine this leading term as a negative x cubed, then remember what is a negative 2x cubed? Negative 2x cubed is like this. Negative 2x cubed itself. So here it says when x is very large, for example, let's label this is a million. Million, okay. This is negative million. then it will be like this. The graph is more or less like this. You just cut the part from negative to x cubed, because when it is very large, you see it's like this. Okay, in the middle it will change, and we only say it's more or less like this. Okay, so when you use your pen to sketch it, you can just copy the graph, the shape of the graph. Okay, so that's what we mean when it is x is large negatively or positively. This is called the AND behavior. The AND behavior. And in the book, they borrow some notations from the calculus. They say, you see here, when x approaches negatively left, the value will be bigger and bigger. So we say the f is unbounded in the negative direction. And in the negative direction. And we use the symbol, the limit x approaches negative infinity. This means x is negatively large as possible. Fx is infinity, means fx is positively large as large as possible. Okay, so we use this symbol to describe that the value of f becomes a larger and a larger number as x becomes a larger negative number. Just like this shape. This is in the mathematical symbol. It's just we write this way, and here we write the other. When x approaches positive infinity, positive. This is negative infinity. To the left is negative infinity. To the right is positive infinity. Fx approaches bottom. The bottom is also infinity. So this is infinity in the x direction. This is a positive infinity in the y direction. This is a negative infinity in the y direction. This is a negative infinity in the x direction. Okay? Okay. So you don't have to clearly understand all the concepts of this part, because you will study them again in the calculus, and you will see the precise definition. But here we just get the idea. It will approach infinity, or will be as big as possible. Here will be as negatively large as possible. Okay. Now let's see this problem. Which of the following graphs could be the graph of this polynomial? Let's first get them. This is A, it's B, C, D. Okay. A, B, C, D. So first, and behavior. And behavior fx will be almost x cubed, as up's value of x is very large. X cubed is like this. I'm sorry, x to fourth power, my bad. X to fourth power. So on two sides, the graph should be like the two open arms. Two open arms. So this one is not correct. So D is not right. Okay, so here is the open arm. Here is open arm. Here is open. So it's possible. We only say they are possible so far. So that's the first. And second, this is not right. Second, you see when x is equal to 0, f0 is the 0, 0, 0, 0, negative 6. So you must have the y-intercept negative 6, a negative number at least. Here we don't see the unit. So this is a positive. So A is not him. A is not correct. So you have B and C. You have B and C. Now let's see this. For this one, it has 1, 2, 3, 4. It has 4 zeros. It's fourth degree. Degree 4. It's okay. Here 1, 2, 2 zeros. 4 degree. It's fine. At least we cannot say no. And then we see the number of the turning points. Here we see 1 turning point, 2 turning point, 3 turning point, 4 turning point, 5 turning point. When you see 5 turning point, then the degree should be greater than or equal to 6, at least 6. But here it's a degree. The degree is only 4. It's not at least 6. So C is not possible. So A, C, D are all not possible. So B is the unique possible case among those 4 cases. We don't say it's a correct formula, but we just say among those 4 things, these 3 are impossible. Only B is possible. Okay, so that's our identification of the graphs. So we use the and behavior, we use the y-intercept, we use the number of the turning points. Of course, we also use the number of the zeros, but that one cannot remove the wrong solutions. Okay. And then let's try to analyze the graph of polynomial. Basically, we want to see how to sketch the graph of a polynomial. Okay. So let's see the function. We have a function x. Fx is a 2x plus 1, x minus 3 squared. Okay, so step 1, and behavior. To get and behavior, we need the highest term, the term with the highest degree, the leading term. So we have to multiply it. So it's a 2x plus 1. Here, a minus b squared is a squared minus 2ab plus b squared. So this is x squared minus 6x and plus 9. And you continue the computation. So 2x cubed minus 12x squared plus 18x plus x squared minus 6x and plus 9 is 2x cubed minus 11x squared plus 12x and plus 9. Okay, so this is the polynomial in a standard form. And then we see that this is the leading term. So the polynomial, so fx behaves like y equal to 2x cubed for large values of absolute value of x. So what is 2x cubed? 2x cubed is like this. So basically, when you finally get the graph of the polynomial, if you cover the middle part, you should see this part and this part in the graph. Okay, you just cover the middle part. Okay, and step 2, xy intercept. Y-intercept f0, 9. To find the y-intercept, it's easier. You just let x be 0, you find the constant term, 9. X-intercept are the zeros. X-intercept are the zeros, so you get negative 1/2 and 3. Negative 1/2 and 3. You just find the 0 from each factor. And then you will decide the multiplicity. Of the 0. So x-intercept already gave us the 0. So the negative 1/2 is a 0 of multiplicity 1, 2x plus 1. So the multiplicity is 1. And 3 is a 0 of multiplicity 2. Okay. Okay. Step 4. This one has degree 3. So graph fx has at most 2 turning points. Degree 3, 2 turning points. Okay. And later you are going to study the behavior near 0. Near negative 1/2. Near negative 1/2. How do you get negative 1/2? Negative 1/2 comes from 2x plus 1. So you will keep 2x plus 1. You will study x minus 3 squared. X minus 3 squared is close to, you just let x be negative 1/2. So you get negative 1/2 minus 3 squared. It's a negative 7/2, and squared is 49/4. 49/4. So near negative 1/2, the non-zero part is close to 49/4. So fx is close to y equal to 49/4 times 2x plus 1. So it's a straight line. When it is close to negative 1/2, it looks like a straight line. Okay, and near what? Near 3. Near another one. Near 3. So 3 comes from x minus 3 squared. So you will keep this term. You will study 2x plus 1. Near 3, x is 3, so 2 times 3 is 6 plus 1, 7 is close to 7. So fx is close to, here you replace 2x plus 1 by 7 and x minus 3 squared. So it's close to a quadratic polynomial. Okay, so this is the behavior near 0. Okay, now let's put all the information together. Let's try to see. Okay, first we know that the intercept -1/2 3, and we know the y-intercept 9. So 9 is the largest number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's y-intercept. The x-intercept 1, 2, 3. This is a 3. Once here, -1/2 will be here. This is -1/2. Okay, and check here. When x is near 3, it's like the 7x minus 3 squared. 7x minus 3 squared is this way. Is a parabola opening up. The leading coefficient is positive. It's opening up. Okay, and when it is -1/2 is close to this linear function. So linear function. So just when they are very large, it will eventually have, check this picture. It will eventually have this shape and this shape. Okay, so it's still very the information is limited, and between 3 and 0 there's a big gap, a big step. You just try to evaluate at 1 what is the value, what is f1. So first you label those important information you already know, and if you want to connect those information together, you're going to find the supporting evaluation between this big gap. So 0, 1, 2, 3. Okay, so we evaluate f at 1. When x is 1, you check the function. 1 times 2 is 2, plus 1 is 3. 1 minus 3 is -2, square 4. 4 times 3 is 12. So this is equal to 12. At 1, it is 12. Okay, 9, 10, 11, 12. Oh, wow. It's here. And if you still confused, you check 2. At 2. At 2, you will see it is equal to 5. Okay, so it's small. 1, 2, 3, 4, 5. 5 is here. So it means it looks like and this part is already small enough. It's my bad. I should. Yeah. And this part I just connected. Okay, so this is the graph of the function. It's the graph of function. Right? Understand? So how many steps do we have? We have 5 steps. Step 1, under behavior. So we know what is a shape outside the certain interval. Under behavior, x, y intercepts the zeros of multiplicity. It touches x-axis or cross x-axis, and the turning point. You see here it has 1 and 2 turning points. And then you have behavior near 0. So when you have those 5 steps, you can label them, and if you want to connect those pieces of graphs, you can insert some additional information at 1, at 2, and you will see it up, and then eventually it goes down. It's not like from here directly go down. Okay? Okay, let's use a similar process to find another, to do another example. Okay, so we have fx is x squared, x minus 4, x plus 1. X minus 4, x plus 1. Okay, so step 1, and behavior. And the behavior, you have to multiply it out. You do the multiplication, you will see it is what it is. Let's do the computation. So x cubed minus 4x squared, x plus 1, x to 4 plus x cubed minus 4x cubed minus 4x squared, so it's x cubed minus 3x cubed, x to 4 minus 3x cubed and minus 4x squared. Okay, good. Yes. Okay, so the graph of fx is similar to the graph of x to 4 as x is large. So x to 4 has a graph like this. So in the future, after you sketch it, you cover the middle part. On two sides, it should be like this. Okay, so that's what we say, and behavior. Okay. And step 2, xy intercept. X-intercept f0. f0 is 0. You let x be 0, 0 times whatever is 0. It's a y-intercept. And x-intercept, fx equal to 0. You solve for it. So you get x squared, x minus 4, x plus 1 is equal to 0. You get x squared is 0, x is 0. X minus 4 is 0, x is 4. X plus 1 is 0, x is negative 1. So you have 3 x-intercept. And multiplicity. Zero has multiplicity. 2. 4, negative 1 have multiplicity. Both 1. Power. They have the same power, 1. Okay, so the multiplicity. When we have the 0 and the multiplicity, we're going to study the behavior near 0. Okay, so near 0, x is 0. So this is negative 4, this is a 1. So fx is close to negative 4x squared. 0 is from x squared, so x squared term is kept. You only let x be 0 for the second term and the third term. Okay, and near negative 4. Near negative 4, positive 4, I'm bad, positive 4. Near positive 4, x minus 4, this term is kept, and you have x squared. X is 4 squared is 16. X is 4, 4 plus 1 is 5. 5 times 16 is 80. So it's 80 times x minus 4. And near negative 1. Negative 1 comes from x plus 1. So you keep this term, and you study this part. Negative 1 squared is 1. Negative 1 minus 4, negative 5. Okay, so that's the behavior near 0. Okay, we another thing, the number of turning point, 5 turning point. So this is a polynomial of degree 4. The graph of f has at most 3 turning point. Has at most 3 turning point. Okay, now let's try to connect them. So you will have 4, -1, 0. So 1, 2, 3, 4, 4, 0, -1. So you have this point, and this point. And 0 has a multiplicity 2, so the graph will touch the x-axis. And at 0, near 0, the function is like negative 4x squared. So negative 4x squared is this way. Okay, so negative 4x squared, it touches x-axis. And when you have the graph near 4, it's like a straight line. When you have a graph near -1, it has a small segment. Okay, and okay, now let's try to connect them. Between 0 and 4, there's a big step, so you can evaluate at 1, 2, and 3. You do the evaluation, and you do the evaluation. Here we can do the whatever evaluation we can try. Let's try f of 1. What is f1? f1 it's 1 squared times 1 minus 4 times 1 plus 1. So this is 2, it's a -6. Well, sorry, 1, 2, 3, 4, 5, 6. And the 1 is here. f2, 2 squared, 2 minus 4, and 2 plus 1. 2 squared is 4. 2 minus 4 is -2, times 4 is 8. 3 times 8 is -24. Holy. It's very negative. Very negative. 2 is very negative. I'm not going to sketch. Well, let's rescale it. So it will be negative and even more negative. f3. 3 squared and 3 minus 1. 3 minus 4. 3 plus 1. 3 squared is 9. 3 minus 4 is -1. 3 plus 1 is 4. 4 times 9, 36. -36 is even big. Small. So it's like this. And here you just connect them. And then when it's greater than 4, less than -1, you use this under behavior x to 4. It's like this. So you see that you already have 1, 2, 3 turning point. You already have 3 turning point. You cannot get a lot of up and down process, because whenever you have an up and down process, you will increase the turning point, the number of the turning point. Okay, so that's the rough idea to sketch the graph of a polynomial. Okay, so in this section, the final goal is to sketch the graph of some simple polynomials, not very complex. You must do some practice. And understand the process and try to completely finish 1 or 2 examples and see what is the graph of a polynomial. So there are only 5 steps: under behavior, xy intercept, multiplicity, behavior near 0, and then the number of the turning points. Okay, so we stop here. we finished the section 5.1.